this recording will go over the Introduction to Microscopy PowerPoints. The type of microscopy or microscope that we use in the microbiology lab is a bright field light microscope. And to be more specific, the light is going to be visible light microscope. It is called bright field because the background is going to be lit. The purpose of a microscope is to enlarge a specimen. Another feature of a microscope is that it has to not only enlarge the specimen, but it has to resolve it, meaning it has to make it clear and sharp. This is called resolution. So a good microscope will not only have good magnification, but it will also have good resolution. The microscopes that we use have 4 distinct parts. At the top, there's the head that holds the oculars. There is an arm that holds the cord. And when we pick up a microscope, we always pick it up by the arm and we put the other hand on the base of the microscope. The base holds the stage of the microscope, which is a table-like structure where the specimen is going to be placed. When we store the microscope, we always store it with the arm facing out so that we can pick it up easily next time. We never store the microscope with the oculars out because that could potentially damage the oculars. Looking again at the parts of the microscope, the head of the microscope is going to hold the oculars. The oculars are the contraptions that we're going to look through when looking at the specimen. Our microscopes are binocular microscopes, meaning that it has 2 oculars. And when we use the microscope, you should always use both oculars. Attached to the top of the head is the revolving nosepiece, which holds the objectives. The objective lenses each have a different magnifying lens. So there will be 2 parts of the microscope that are going to hold magnifying lenses. The objectives and the oculars also have magnifying lenses. Continuing on, we're looking at the base of the scope, and we're looking at the left side of the base. Our microscopes on the left side have 2 knobs. The large knob is called the coarse adjustment knob. When we move this knob, when we rotate the knob, we can move the stage up or down in large enough increments that we actually see the stage moving up and down. Notice that the only time we use the coarse adjustment knob is when we're trying to find the specimen initially at the beginning. So the only time we use this coarse adjustment knob is when we're finding the specimen with the 4X objective. After we have found this specimen, we do not use the coarse adjustment knob anymore. Sitting inside the coarse adjustment knob is a smaller knob called the fine adjustment knob. When we rotate the fine adjustment knob, it also moves the stage up and down, but it does so in such small increments that we don't see the stage moving. We use the fine adjustment knob with any of the objectives after we find the specimen when we're trying to make the image clear. So let me just restate. We use the coarse adjustment knob when we're first trying to find the specimen. We try to find the specimen with the 4x objective. After we find the specimen, we drop the coarse adjustment knob, and from that point on, the only knob that we use is the smaller fine adjustment knob. As we switch objectives, we do not touch the coarse adjustment knob again. We continue to fine adjust only using the fine adjustment knob. Also on the left side of the microscope, we have the on and off switch. And behind the on and off switch is a knob called the rheostat, which controls the amount of light that is going through the specimen. Typically, the rheostat is left closed when the microscope is stored. So when you initially use the scope, you not only need to turn on the switch, but also you are going to need to open the rheostat by rotating it in the clockwise direction. Notice that as we increase magnification, you're going to need to increase the amount of light that goes through the specimen. From behind, we can see the cord and we can see the microscope number of our scopes. This is the right side view of the microscope. And on the right side, we can see below the stage control knobs that are going to move the stage left and right, up and down. So we can move or slide to view different parts of the specimen. Also notice that in the middle of the stage, there is an opening. Through the opening, we can see the condenser. We place the specimen on the stage and we hold it with the stage clips. Then we move the specimen so that it is placed on top of the condenser. The condenser allows for light to shine through into the stage and into the through the specimen. Okay, this is the front of the microscope. And we can see another view of the stage. And notice that below the stage, there is a circular contraption. This is called the condenser. The condenser is going to gather the light that is coming from the light bulb below, and it's going to shoot the light to the specimen sitting above on top of the stage. It is hard to see in this picture, but there is a little lever that is found at the edge of the condenser. The lever controls the iris diaphragm mounted inside the condenser. The iris diaphragm can also be used to regulate the amount of light that goes through the specimen. So there are two ways to control the amount of light that goes through the specimen. We can use the rheostat, or we can use the iris diaphragm lever mounted on the front of the condenser. Our scopes are called compound scopes. The reason why they're called compound scopes is because they have two sources of magnification, meaning there will be two sets of lenses magnifying an image. The first set of lenses that will magnify the image as the specimen sits on the stage is going to be the objective lens that's in place. The second lens that will magnify the specimen is going to be the oculars. So there are two sets of magnification lenses that will be magnifying the image. The first set will be the one found on the objective lens. The second one will be the one found in the ocular lens. you should know what we mean by a compound scope, and you should be able to explain why our scopes are called compound scopes. So the magnifying lenses will be magnifying the image, the specimen, and in a compound scope like ours, there will be two sources of magnification. The first source will come from the objective lens in place, and remember there are four different objective lenses in our microscopes. The second magnification is going to come from the ocular lens itself. So in order to calculate the total magnification, or TM, of your specimen, we need to account for the two sources of magnification, the ocular and the objective. So you should be able to calculate the total magnification of your specimen based on the two lenses that are being used. If you have the scanning or 4x objective in place, it is magnifying the image 4 times. Multiply that 4 times magnification to the 10 times magnification of the ocular lens, and you have a total magnification of 40x. So when the scanning objective lens is in place, the image has a magnification of 40 times. As you move the objective to the next magnification, this is the 10x, is called the low power lens. It magnifies the image 10 times, which when it's multiplied by the 10 times of the ocular, we achieve a total magnification of 100x. So when the low power objective is in place, the specimen is being magnified 100 times. As you switch to the next highest power, which is the high power lens, the magnification increases to 40x, which when multiplied by the 10 times magnification of the ocular, we're looking at a magnification of 400x. Finally, as we switch to the highest magnification, which is the all immersion objective, now the image is being magnified 100 times, which when multiplied by the 10 times of the ocular, the total magnification will be 1000 times. So the maximum magnification that we can achieve with our scopes is 1000 times magnification. You should be able to determine the magnification of a specimen given the objective in place and knowing that our oculars have a 10x magnification. So you should know the total magnification under the scanning objective, the low power, the high power, and the all immersion. You should also know the names of each of the objectives and the magnification that each of them carries. Now let's talk about the concept of resolution. We mentioned initially that resolution is the ability of a microscope to resolve an image and make it clear and be able to see the details of the image, to resolve the image. A microscope with poor resolution will not be able to give us clear details of a specimen. So for example, in this example right here, what we see is one structure with a little indentation in the middle. Whereas with better resolution, we can actually see that these are two different cells close together. So now we can resolve the image as two objects, not one object with an indentation in the middle. The problem with resolution using visible light microscopes is that in order to improve resolution, the rays of light must be able to travel in between objects. if the wavelength of light is too large, it cannot travel in between the details of the specimen, and the image will have poor resolution. On the other hand, if we use wavelengths of light that are very small, they will be able to travel in between the minute structures of the specimen, and you will be able to resolve the specimen and get better resolution. So the limiting factor when it comes to resolution is the wavelength of visible light. And you can see here that as we look at the wavelengths of visible light, the larger wavelengths are the ones that fall in the red, orange, yellow color. Whereas when we go down to the blues and purples, now we have a small wavelengths. So in order to improve resolution with our microscopes, the scope is actually using a purple light to shine on the specimen. We do not see that. We think we're looking at a white light, but we're not. The microscope is actually using a purple light because a purple light will create better resolution as purple light has smaller wavelengths. So that is one feature of the microscope that allows us to improve the resolution. The other feature that improves resolution in our scopes is the use of oil immersion on the 100x objective. So notice that the 100x objective is called the oil objective. That's because when we use the objective, we're going to put a drop of oil between the specimen and the objective. And we will do this in the lab, and we will teach you how to use a oil immersion objective. So you should know the two features that improve resolution in our scopes. Now, remember that the first thing we need to do, the first order of business when we are using a microscope is the cleaning of the scope. When we clean the scope, we use lens paper. We never use anything that is not lens paper to clean the lenses of a microscope. Remember that we taught you that you needed to use lens paper, and the order in which the lenses are cleaned is always the same. We first clean the oculars. With the same paper, we proceed to clean the 40x objective. Then with the same paper, provided the 40x objective is clean and it has no oil in it, we can move on to the 100x objective. Sometimes the previous student did not clean the objectives properly, and the 100x objective may still have oil in it, in which case the student needs now to put in a little effort to make sure that the oil is completely removed. Even a worse situation is if the previous student allowed oil in the 40x objective, which is something that should never happen. Okay, so the 40x objective should never have oil in it. However, sometimes students carelessly allow for oil to be put in the 40x objective. It is then even more pressing not only to clean the 40x objective with a lens paper, but also to clean it with a special cleaner that will completely remove the oil out of the 40x objective. Another item that has to be cleaned prior to use is any prepared slide that we may be using. Prepared slides can be cleaned with any type of paper. Lens paper is too expensive, so any type of paper like the one we have on your tables in the yellow bands will do to clean the prepared slides. But remember, lenses are only cleaned with lens paper. Slides, on the other hand, can be cleaned with any type of paper. Do not use lens paper, however, because lens paper is too expensive. The next order of business is to put the lowest objective in place, which is the 4x objective. You place the slide on the stage and hold it with the slide clips. And then we're going to bring the stage all the way up using the coarse adjustment knob. So we're moving the stage up all the way with the 4x objective in place, and then we'll proceed to look through the oculars. As we bring the stage down slowly using the coarse adjustment knob until we find the specimen. This is the only time that the coarse adjustment knob is going to be used, is with the 4x objective as we're looking to find the specimen. Notice that we're moving the stage down, so we're moving away from the oculars. Once we find the specimen, or what we think is the specimen, we can confirm and make the specimen clear by using the fine adjustment knob and fine focusing. So again, we are starting with the stage all the way up at the 4x objective, the scanning objective in place. Make sure the condenser is also all the way up. Sometimes the previous students may have been playing around with the condenser and may have not left it all the way up. There is a knob that will control the position of the condenser. So the stage up, 4x objective in place. Now we're going to use the coarse adjustment knob to slowly move the stage down until we see the specimen. So once we see something, we're going to use the fine adjustment knob to fine adjust the image to make it clear. If you move the fine adjustment knob in one direction and that is not making the image clear, rotate it to the opposite direction. The fine adjustment knob does not have to be moved a lot to make the specimen clear. Just a slight movement should be able to clear the specimen. Remember to center the specimen in the middle of the field of view. And just to make sure that what you're looking at is a specimen on the slide, you need to move the slide and make sure the specimen moves when you move the slide. If the specimen doesn't move when you move the slide, that means you're not focused on the slide. And that is not the specimen you're looking at. So you need to go back and bring the stage down a little bit further to actually find your specimen. Remember that the fine adjustment knob is used to fine focus only. And the stage knobs can move the specimen up and down or sideways. Now, you have found the specimen and you have put it in focus. Now you're ready to increase the magnification. What you're going to do is, without touching the coarse adjustment knob again, you're going to rotate the nose piece to the next highest magnification, which will be the 10x low power objective. Okay, so again, it is important from this point on not to touch the coarse adjustment knob again. The reason why is because as we increase magnification, the objectives become longer and longer and longer. And if you touch the coarse adjustment knob, you are risking crashing the stage against the objective. and that could potentially ruin the very expensive high magnification objectives. So just to reiterate, don't ever touch the coarse adjustment knob after the 4x objective. Now, a couple of features that you have to be aware of on your microscope is that our microscopes are parcentral. What that means is that the center of the field of view remains the same regardless of the magnification that you're using. So if this is the field of view under the 4x objective, as you increase magnification, the field of view becomes smaller, but the center remains the center. So the 10x and the 40x will have smaller fields of view, but notice that the center remains the same. And that's why we tell students to always move the specimens to the center of the field of view. The other feature of our microscopes that make them very expensive is the parafocal feature. The parafocal feature allows the microscope to retain focus as we switch objectives. That is why we do not have to use the coarse adjustment knob under every objective, only under the first objective, the 4x objective. Once we have found our specimen and we've made it clear, we can switch to the 10x objective and it will remain clear. After, we may need to fine adjust it a little bit, but the image will remain clear. Then we switch it to the 40x objective. The image is still there. We may need to fine adjust, but we do not need to find the image again from scratch. So you should know, what do we mean by a parafocal scope? What do we mean by a parcentral scope? Another feature of the scope is the working distance. The working distance is the distance between the objective and the stage. And notice that as magnification increases, the objectives become larger and the distance between specimen and objective becomes smaller. So the distance decreases as magnification increases. So the working distance decreases as magnification increases. We mentioned that the diameter of the field of view is going to decrease as magnification increases. So we're looking at a smaller and a smaller area as we are increasing the magnification. That's why it's always important to move the specimen to the middle of the field of view before switching to a higher magnification objective. Finally, after using the microscope, you need to put the prepared slide away in the correct slide tray. You might want to clean it before you return it to the slide tray. The oculars are rotated, and we're going to put the 4x objective in place. We're going to use the coarse adjustment knob to move the stage all the way down. We're going to wrap the cord around the arm and store the microscope with the arm out. This concludes the PowerPoint on microscopy.